Superconductivity was discovered in 1911. It's a fairly complicated physical principle, and it took a long time for the scientific community to work out a successful theory. One issue was that that theory had very well-defined predictions, and one prediction was that the maximum temperature at which we could observe superconductivity was very low. So when we developed a superconductor that had a transition temperature close to that temperature, people stopped looking. So this very successful theory inhibited the development of superconductivity, basically because the theory was so successful. I'm David Cardwell. I'm the head of the bulk superconductivity group in the Department of Engineering at Cambridge. We make large bulk superconductors to generate large magnetic fields, and our work is to look at the properties of those materials and how we make them better. There are basic differences between a superconductor and a normal metal. A normal metal is the thing that carries electricity for a whole host of applications like power transmission, overhead cables, electricity that's carried around a laboratory, for example, to a home. The problem with normal metals such as copper is that it gets warm when it conducts electricity, and they're losses, and those losses have to be provided from some energy source. Superconductors carry electricity with very low losses, up to 15% lower losses than one would observe in copper, for example. So if one were to strip out all the copper supply cables to the UK, there'd be an enormous absolute saving in energy. Certainly into megajoules worth of energy and possibly gigajoules. And that means that the energy requirement totally from the UK would go down, therefore fossil fuels would last longer. A good example is the city of Tokyo, where electricity is carried via copper cables under Tokyo. The problem is the demand for electricity in Tokyo has now exceeded the capability of the cables that supply it. So one option is to take out those cables and replace them with superconductors. Superconductors per unit cross-sectional area can carry up to 100 times more current than copper. So therefore you increase your power transmission capability without having to dig the streets of Tokyo up. A superconductor has got potential to generate large magnetic field. If you take a copper solenoid, for example, so it's wire wound, you apply voltage between the two terminals and the current flows. If you remove the voltage, then the current stops and the field disappears. If you could make that coil out of a superconductor and you could short out the ends, then you would generate a large stable magnetic field. And those fields can be very much bigger than the fields that one associates with copper wire wound solenoids. The most well-known applications of superconductors are things like magnetic resonance imaging, or MRI, where a high magnetic field can be used to get a very good image of the human brain, for example. Another application that's well known is that of the levitating train, where we get stable levitation between a rail and a train produced by a high magnetic field generated by a superconductor. That gives us no contact resistance, which enables high-speed, stable transportation. In 1987, a superconductor which had a transition temperature greater than the boiling point of liquid nitrogen, which is minus 196 degrees C, was discovered. This was an incredible discovery. For the first time we had a material that we could use liquid nitrogen, which is freely available. It's in the atmosphere, it's not a pollutant, it's abundant, it's cheap to liquefy, it's cheap to use, it's stable, it doesn't boil off. We could start to imagine practical applications on a large scale since we had this material with this very high transition temperature. One of the problems was that yttrium barium copper oxide, as the material was, had a number of challenges, and they were to do with processing. One problem with YBCO is that it contains small grains, and current can't pass from one grain to the next within the microstructure, and that means you can't generate large magnetic fields because current won't flow over a large area. What we've been doing for about the past 15 years is developing a method to generate large single-grain bulk YBCO and related compounds. So we've got a melt processing technique where we semi-melt the material, we then regrow it in a controlled way, and it just gives us one single grain. Now that single grain therefore contains no grain boundaries. When we apply a magnetic field, we can get currents to flow over a very large length scale, and therefore they can generate a large stable magnetic field. Any magnetic levitation application would be supported by bulk materials, things like magnetic separation, where we have a liquid or a slurry, we have a magnetic species in there, we want to remove it from its background. A strong magnetic field, a large gradient is what's required. These materials are ideal for that application. Also things like low resolution MRI, where you need a large background magnetic field and you get an MRI signal. You don't necessarily need to produce an image, but you may get a spectrum. It would be a very cheap, very easy, very convenient way of producing a magnetic field of that nature. Have in mind an imaging device or a magnetic resonance recording device in every doctor's surgery for very quick diagnosis of things like joint issues and joint problems, which then could be referred to a full scan. The applications of bulk superconductors and other superconductors are extremely exciting. However, we have to remember that we still have a materials problem to solve. There's materials development, and the materials are good at the moment and they're on the verge of commercial application, but there's still some way to go. If we think of the transistor and the laser, the decades that they took to develop into usable devices, superconductivity is exactly the same. So although potential applications should be achievable within 5 years, certainly within bulk superconductors, there's still a lot of materials development that needs to go on. And we need to remember that. We need to make products better, more efficiently. We need to think about products that we today haven't even thought about because these fields have not been available at the required temperatures. So that's going to take a bit longer. That's going to take 10 years at least. But then even after 10 years, there are still new and exciting developments that will evolve from this technology as we continue to develop it.